Okay, so what exactly is triangle congruence? So congruence in general means that two or more things are the same. They're exactly the same. So triangle congruency is when two triangles have the exact same three sides and the exact same three angles. So the same side lengths and the same side angles. So the equal sides and angles don't necessarily have to be in the same like position, like they can be oriented differently, but they're still congruent because they have the same sides and the same angles. So here, these triangles with the red letters, they're 5. You can see that they're like they're 90 degrees and they have the same angles. That's just implied. And then here you can see that this length is 5, this length is 3, so this length and this length is 4, and they're the same, but they're just mirror images, but they're still the same triangle. And here these tick marks indicate that these are the same sides. So these are the same sides. AC and DF are the same side. AB and DE are the same side, and CB and FE are the same side. And same with the angles, like it tells you like this angle is the same as angle A is the same as angle D, angle C is the same as angle F, and angle B is the same as angle E. So they're congruent. Okay, yeah, so congruent triangles are an important part of our everyday life and world, especially for reinforcing structures, buildings, all of those. And if two triangles are congruent, if they're completely identical, and this means that the matching sides must be the same length and the matching angles must be the same size, they must be the same angle. So like we just said before, and this like equal sign with the squiggle on top, that means that they're congruent. So now we're going to look at the types of congruency. So SSS, there's many different types of congruency. So this right here, SSS, it stands for side, side, side. We're just too lazy to say side, 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 so we say SSS. And when two triangles have the exact same sides, that means they are SSS congruent. So when all three pairs of the corresponding sides are congruent, when they're all the same, then the triangles are congruent. So if the sides are the same, the angles are also going to be the same. So you don't have to say like it's already implying that the angles are the same. So the sides and angles are all the same. Okay, so the next is side angle side congruence, SAS. So keep in mind the order actually matters. So side angle side, like one side, one angle and one side are the same. They're corresponding to the same angles and sides of another triangle. So when two pairs of corresponding sides and the corresponding angle in between those two indicated sides are the same, then the triangles are congruent. And ASA, angle side angle, angle side angle. So when two pairs of corresponding angles and the corresponding sides between them are congruent. So if you're given two angles in a triangle, like just try to visualize this. If you're given two angles on a triangle and you're given the side length in between those two angles, and if you have two triangles and those are the same, the angles and the side in between them are the same, then they're the same triangle, they're congruent. And then angle side. When two pairs of corresponding angles and one pair of corresponding sides, it doesn't have to be in between the angles. It's not in between the angles, that's why it's AAS. When they're the same, then the triangles are congruent, okay? And then the last one we're gonna look only applies to right triangles. So when it's called HL, hypotenuse leg congruence. So this is a special one just for right triangles because like right triangles are the only triangles that have hypotenuses. When the hypotenuse and a pair of corresponding sides of the right angles are congruent, then the triangles are congruent.
Stop right here and share a whiteboard right now. So So the first thing we have is SSS. Let's say we have a triangle like this. If all the sides are the same length, then the orientation might be different. It may look like this, right? But it's still the same triangle, just flipped. So as long as all the sides of a triangle are the same, the angles can't be different. Next one is angle side angle. So let's say we have a side right here. This is our stationary base, and we have angles like this. So if these angles are the same, these sides have to meet up at the same point. So there's no way that you can change this so that the side is a different length, because the angle is the same. These angles are fixed, so they just go up and have to meet. Keep in mind the origin point, right? We have an angle here, side, and the side sandwiched in between the angles. We also have SAS, side angle side. So if we have a fixed angle here, this is fixed. So, and then these two side lengths are also fixed. That means there's only one way to complete the triangle, which is draw a line between these two. So let's say you have another example where it has a fixed angle and two sides are the same length. You have to complete the triangle the same way. This. And now we also have a what's the next one? Let's see. Angle side of AS. So we have two angles here. Let's see, we have angle 1 here, angle here. Okay, sure. Let us know after the end of class, like you can let us know which proofs you need, okay? Or after the presentation, when we're giving out the work, the classwork and homework, then you can ask questions on like if you have individual problems. So we know that this side actually currently isn't fixed. We can call this x because it's a variable. It's not fixed right now. But this side is fixed. So that means this has a certain length. So x has to adjust, and this also tells why this also isn't fixed right now. But these have to adjust to make this a complete triangle. So if you have anything else like this, we know this angle here, this doesn't really matter right now. You have another fixed angle right here, and the fixed side. That means y and x have to make it so that it's a complete triangle. I'm clear my screen right now. We also have hypotenuse leg. This has to be for a right triangle. So this is a hypotenuse, and either of these are legs. So you know from Pythagorean theorem, if we know the hypotenuse and one leg, we can find another leg, right? We have leg 1 squared plus leg 2 squared equals hypotenuse squared. So if we know what leg 1 is, and we know what hypotenuse is, we can easily determine leg 2. So this could either be a SSS, because this is L2 and we know it, or it can be yeah, or because we know that they're fixed angles, it can be SAS, anything like that.
So basically, I think if it's HL, if HL also indicates SSS congruent, because if you're given two sides of a right triangle, then the other side you can find out using the Pythagorean theorem, and it's going to be the same in both of the triangles.
Yeah. So we noticed that we covered these congruencies, right? Does anyone have another? Does anyone think we left anything out? And does anyone notice that we didn't cover a combination of the letter A and S? Okay, so it's okay. We'll go over it later in the presentation. But there is one combination of A and S that doesn't work.
Again, like we just went over, these are some really good examples. This is like a reference slide you should look back to if you ever like are confused or need help. So yeah, I think SSS is pretty simple. You guys will be able to grasp that really quickly, but here you can see how in the second from the leftmost example, this middle top one, it's SAS. So you're given this side with 2 ticks. Side AC it corresponds to this other triangle, and triangle XYZ, it corresponds to side XZ. They're the same length. And side YZ with this tick on it, this single one, and side BC with this single tick are corresponding. And then therefore, I mean, this angle we're given, angle ACB and angle YZX are the same. So these triangles are the same. See, because we're given an side, angle, and then again, side, angle, side, and the other triangle too. And then here we have angle, side, angle. So I like to think of it as like a sandwich, like the angle and side and angle, like the angles are the bread and the side is the filling. So the angle is given and then the side is sandwiched in between, and the angle is like outright like on the other piece of bread. So angle E and angle C, no, angle E and angle B correspond, and angle F and angle C correspond, and then side EF and CB correspond. They're the same triangle. And then AAS, angle side. There's not really any sandwiching going on here. So it's A. We're given angle A, and then this double like marked angle B, and then we're also given angle side AC. So side AC corresponds to side XY, side angle B corresponds to angle Z, and angle A corresponds to angle Y. So these triangles are also congruent. And then here again, we have HL, hypotenuse leg. You can see that these are both right triangles. And side AB and XY are the same. And we already know that side angle X and angle A are going to be the same because they're both, 90 degrees. And then side YZ and side CB are also the same. And we can prove this using the Pythagorean theorem that side XZ and side AC are the same. And therefore all the angles will also be the same because the sides are all the same. SSS.
So here's a link. Okay, so HL and AAS. So for HL, that's only for right triangles. So we know that any of these apply to right triangles, like SSS, SAS, like they all could apply to right triangles, but HL doesn't apply to anything else. So let's say I have a non-right triangle, right? So we have, let's say this triangle that's not right. So we know that there's no hypotenuse because the hypotenuse is it's only the long side for the right triangle. So we know this is a hypotenuse on this triangle. Like even if we want to prove, let's say we have an angle here, we have a side here. There's no hypotenuse here, and then so we can't really call any of these sides legs. That's why. And this is a right triangle. We know that so we know that the angles are the last side is given by a by Pythagorean theorem. And when we come back from a break, we'll go over more of Pythagorean theorem. So here's more practice problems if you want. Okay, so something's off. So as I asked earlier if anyone knew any combinations that we didn't go over, and here they are. We have SSA, which doesn't exist because an angle on two sides does not definitively tell us if two triangles are congruent, and AA doesn't work because the sides length we have nothing fixed about the sides. So here we can have similar triangles but not congruent. So here's the explanation for why SSA doesn't work. Let's say we have a fixed side here, right? No worries. We have another fixed side here. Fixed side here. And then, let's see, fixed side here. And then, you know that this angle, yeah, we have this angle here, and the two fixed sides. So you may see, oh, just draw a line here from this to this. This to this, and then we're done. But then there's another case where we have this fixed side here, an angle here, but there's nothing to determine what the angle will be right here. So this can be anything. So I can have the same fixed side. These two are the same length still, right? But then, and then this can still connect. But these are not the same triangles anymore. That's why SS8 doesn't work. Here we have more solving problems with ratios. So Suresh owns a dog training facility and wants to create a ramp for the dogs to push up the platform. So he wants to raise the ramp to rise 10 centimeters for every 30 centimeters of horizontal length. And the height of the platform is 180 centimeters. So how long should the ramp be? So we already have the answer up here, but if anyone wants to try it on their own, then go ahead. I'll give you 2 minutes here. Okay, so I'm just going to go over it since it's right here. And so we can do this by setting up equal fractions, like 10 over 30 equals 180 over x to solve for x. Or you can do it this way, just both ways are to find the ratio in between them. So we know that there's an 18 scale factor, that's the ratio. So we see 10's here, and then this is 18 times bigger. So we know that this length is also 18 times bigger than 30. So it'll be 540. Okay, so this one doesn't have the answers. So a Javander is volunteering as local hospital, and he's helping them build a wheelchair accessible ramp. The requirements are that the ramp should be 30 centimeters tall for every 50 centimeters long. He built the ramp at a length of 2 meters. So how tall should the ramp be? Yeah, so try this problem on your own. So I see Zara just joined. So I'm going to, while we're doing the problems, I'm going to put the Google Classroom link. So here's the link to a Google Classroom. See? So has anyone gotten the answer? You can type in the chat or say it out loud if you want. Okay, so I'm just going to share my screen and go over this problem. So this is 30 centimeters, and this is 50 centimeters. And this one is unknown, and this is 2 meters. So once you find the scale factor of this, so there's two ways to do this. One is compare each side to each side. So we can compare 50 centimeters to 2 meters in order to find the scale factor between 30 centimeters and x. Or we can compare 30 centimeters to 50 centimeters and compare the scale factor between x and 2 meters. So I'm going to do the second way. So 30 centimeters divided by 50 centimeters, scale factor is 0.6. So we know that x is 0.6 times 2 meters times 0.6 as scale factor equals 1.2 meters. Does that make sense? All right, so continue with the slideshow. So let's take a look at some similarities. So these aren't congruent, but they're similar instead. So we know that the bigger triangle is exactly 3 times the length of the smaller triangle. So they're similar, they have the same shape, but not the same size.
So now we're gonna look at some angle similarity theorems. So like Justin said before, angle similarity just means that they're not congruent, but they may be like scale copies of the same thing, same triangle. So if we're given two angles in a triangle, this you can just think of, it's just short for AAA because we don't want to write the entire thing out. So if two angles are the same in between two triangles, because the angles have to add up to 180, you can just, that the other angle, the missing angle that's not stated, is like the same for both triangles because they have to add up to 180. So like you can just think of this as AAA or just AA. So if two angles in the triangles are the same, then the triangle is similar. So this is just saying like if the three angles in two triangles are the same, then they're similar. So this is, they're not congruent because they can be like scale copies of the same thing. Like you can have a triangle that had like an equilateral triangle with like equal angles, obviously, but you could have like two of them, but one of them could have like side lengths 1 1 1, but the other one could, if the angles are 60 60 60, then like the other triangle could have side lengths like 300 300 300, because that's just a scale copy of another triangle. So they're obviously not the same triangle because the side lengths are different. So that's why angle is similarity and not congruence.
There's a problem with this. I made it. Give me 1 second. I'm going to edit it in the proportion. Here we go.
Okay, so side. I know we said that this is also like congruence, but this is if they're like proportion. So like I said, like I was talking about scale replicas, like scale models, this is like all three sides are in proportion. So if you have like a triangle that has side lengths like 3, 4, and 5, and you dilated it, like you expanded this, we talked about this last week, I think, dilation. So if we were to multiply each side length, like if we had side lengths x, y, and z, and we dilated it by a scale factor of 3, then the new triangle would be bigger and the side lengths would be 3x, 3y, and 3z. Okay, so it would be like, it would just, that's what we mean by proportion in proportion. They're scale models of themselves, of the sides. And then side angle side, side angle side. This is another similarity thing, but this also, like, this is not the same as the side angle side that we talked about before. So if two sides in a triangle are proportional and the angle between the two sides in the triangle is the same. Yeah. And then these are some examples. So again, SAS, this is similarity. So like we said before, SAS, these two triangles are scale models of each other. So even though like they are demonstrating SAS, this is their proportional scale models of each other. So this can anyone tell me the scale factor of the first two triangles, the SAS? Like what are the side lengths of the smaller triangle multiplied by in order to get the other triangle? You can just put it in the chat or just say it out loud. But yeah, it's right. Okay, yeah, correct. It's 2. It's 2. So the sides are multiplied by 2 in order to get the new triangle. And then AA, angle, or angle, like I said before, you're given one angle like 90 and then 35, and then you'll have to use the angle sum theorem to find the length of the measure of this other angle A, and angle D. And if you do that, 35 plus 90, and then that answer is 125, and 180 minus 125 is 55. So that's what you get the measure of this other angle is. And then SSS, these are scale copies. So this is not a whole number. It's not an integer inflation. It's not an integer dilation. So you have to multiply. You can find the scale factor by 15 divided by 10. So these are corresponding sides, side DF and side CA. So 15 divided by 10 is 3/2. So the scale factor is 3/2, so 1.5. So 8 times 1.5 is 12, and 12 times 1.5 is 18. So these are scale copies of each other. And then I'll copy and paste some practice problems with similarity theorems. Okay, so why are AAS, ASA, and SSA not congruence theorems? So AAS and ASA do not exist because it all simplifies down to the AA theorem. And SSA doesn't ensure similarity in certain cases, such as right triangles. if two sides are proportional and the unincluded angles are the same, then they're similar. Then this is only conditional. So SSA, the reason we don't like include that in our similarity theorems is that in right angles this may apply, but in other triangles it may not apply. So because like if you're given two sides and an angle, then the other side is implied in a right angle, in a right triangle. But in all other cases, this may not always work. This may not always like indicate congruence or similarity. And then, so now we're gonna look at the angle bisector theorem. So we have this triangle A, B, and C, okay? And we make this a bisector just means it's a line. So in Latin, sect means part or split. So we make an angle bisector. That just means we're splitting the angle in half, okay? So we split this angle A in half, and then angle BAD is congruent. It's the same as angle CAD because we're just splitting this angle A in half. So these two angles, like angle BAD and angle CAD, are gonna be the same. And just a piece of theory, when we're measuring angles, the vertex is always in the middle. So CAD and BAD. Okay, so, and then line AD is congruent to line AD, of course, because they're the same length. So this is just proof. I think someone asked for more practice with proof. We're just going over that a little bit. And then angle BDA is congruent to angle CDA. And also another thing about angle bisectors is that like if they're perpendicular to the side they intersect. So they form right angles because we know that line BC is 180 degrees, and then if it's perpendicular, then each of these angles, angle BDA and angle CDA, have to be 90 degrees. They have to be not right angles. And therefore, we can conclude that the two triangles are congruent using angle, side, angle, congruent. So this angle bisector theorem tells us that side AB equals side BC and side BD equals CD. Refer to the split triangle. Yeah, I'm talking about the split triangle.
So,
okay, so now, oh, sorry.
Yeah, so this is like now just practice now, and I think we're taking a little bit longer than usual, and I want to make sure there's time for like individual questions and problems. But so this will all be in the Google Classroom as well. So if you want to look at these problems, it's fine too. And then